Our next talk on state of SSL on the internet in 2010, and it's presented by Ristic, Director of Engineering for Web Application Firewalls and SSL at Qualys. Please give a warm welcome to Ivan.
Thank you. So I'm going to talk today about SSL and in particular about our survey of how SSL is currently used on the internet. What you can see on the screen right now is the agenda. Although it's slightly misleading, I have about 50 slides, which is way too many. So I'm pretty much going to skip through the first half of the talk and leave the slides there for you to use later. And then I'll spend most of my time on the actual survey results, which are really fascinating. There are about 20 slides in the survey, which are packed with information. And we will go through every single of those slides, and I will comment on the results. So, just quickly about myself to give you a reason why you should listen to me. I've spent quite a few years working in security right now, by now, and basically what I like to do is pick on a topic that's not really very popular or covered by other people, and then look deep into it and try to figure out. In a way, I do it as a way of educating myself, because there's no better way to learn about the technology than to go deep and learn everything there is about it. So this is how I came to work on SSL. Like a year and a half ago, or 2 years ago, I wanted to revisit the topic, and I realized that actually there is so little written, so little information about SSL out there for people who are not necessarily interested in the protocol itself, but in using it. And one thing led to another. So what eventually happened is that we started this research effort, which we called SSL Labs, which is just a website, a non-commercial effort where we try to make sense of SSL. So the survey that I'll be talking today is about that and making sense about SSL. So if you go to the SSL Labs website, you will find that we have a number of interesting projects. For example, on the screen you can see the SSL fail model, which is very helpful if you want to understand in which ways SSL can fail. And there are other projects. Most interesting one is the SSL rating guide. One of the first things I realized when starting to look into SSL is it's very difficult actually for normal people who are not SSL expert, to understand if a particular server is configured well or not. So this is how the SSL rating guide was born. And the idea was to have a decent methodology that will basically sum up a configuration of a particular SSL server into a grade. And as you will see later on, the good thing about doing this is that if you give people a single grade, which is a letter from A to F, it's very easy for them to understand if they're doing things well, even if they don't know much about SSL itself. Now, the guide is not an attempt to kind of come up with a perfectly accurate grade, but its main purpose is just to convey a meaning and allow us to compare the configuration of different SSL servers and point and say which server is better configured. Also, what the rating guide does not cover is it doesn't look into the cost, interoperability issues, or performance issues of SSL, which sort of would make it into a much larger project. So the thing about the SSL rating guide, we basically use it as a foundation for our assessment engine. And I think this is the best part about the SSL Labs website, which is a free assessment tool where you can go to the website, you can type in the domain name of your SSL server, and then the tool will actually go inspect your SSL configuration and tell you everything that you need to know about it. So I have some partial screenshots for you here. So you can see that the goal of this assessment tool is to give you the grade. So at a glance, you can find out what's going on. And then also, you will be given full details of every single aspect of the SSL configuration. I imagine we have about 200 data points that we collect from every SSL server. And the test itself is quite comprehensive. So I think there's about 2,000 packets or 200 TCP connections and 250 kilobytes of data that we exchange with every SSL server that we test. Furthermore, we will also look into all the servers that are behind a single domain name, and we will point to inconsistencies in configuration among them. So part of my reason for being here today is that we want to raise, generally speaking, raise awareness about SSL misconfiguration problems, and we want to get as many people as possible to visit our online website and test their own sites. However, we also realized that no one has really looked into how SSL is used worldwide. And then we decided to use the same assessment engine that we have and run it against as many SSL servers as possible. To build the assessment engine is not a trivial task. The one that we have online, we probably spent a year perfecting, because it's one thing looking at reading the documentation and the RFCs and building something from that. It's an entirely another problem actually looking at how things work in real life. So the long period during which the engine was online allowed us to really identify these real-life issues and fix them before we undertake our SSL survey. Anyway, so that's a very quick introduction into SSL labs. The next section of my presentation is about finding the SSL service to inspect. Of course, the challenge is how do you find this service, because there isn't a single registry of service on the internet. And there are various ways in which you can go about doing this. You can, for example, scan large batches of IPv4 address space. You can crawl the internet. You can build a search engine so you can catch all the links that are out there. You can use domain name registrations and then look at each individual domain name and see if it supports SSL, and so on and so forth. Another approach, for example, is to use a browser toolbar, which will basically catch and see where users are browsing. Generally speaking, neither of these approaches is perfect, and it's probably best to combine all of them in order to get the best possible coverage. Generally speaking, it may not be ever possible to build a complete list of all SSL servers on the internet, because there is sometimes a way to, the mapping is not always one-to-one. For example, a single SSL server, even today when virtual SSL hosting is not possible, can actually serve multiple sites and multiple certificates. So in general, you can never really be sure that you're seeing everything. So for our survey, we decided to go with the domain name registrations simply because that was the quickest and most predictable way in which we could get to a large number of domain names and SSL servers. So what we basically did, we collected the complete lists of .com, .org, .net, .info, .biz, and US domain names, and we got a list about 120 million of those, which, because we know there's about slightly less than 200 million registered domain names worldwide, our coverage is about 57%. And I think we got most, if not almost all, top-level domain names, but in the survey we didn't use any of the country-specific top-level names. Also, as an additional data set, we looked at the top 1 million most popular websites, which is a list that is combined and published by Alexa Internet. This other list will give us a much smaller number of SSL servers. However, in a sense, that list is more meaningful because these are sites that people are actually visiting. And because our data set was 120 million, and because our assessment engine takes a long time to assess a server, what we did in the survey, we had a very lightweight first pass. And in that first pass, we wanted to just identify those servers and domain names that are active and that are running SSL. So this section of the talk is actually a sort of a survey within the survey, which will give you some idea of how many domain names there are and how they're used. So for the lightweight pass, we built a very simple assessment program, which basically uses as few packets as possible, doesn't complete even a single SSL handshake, because we had so many domain names to scan. And we managed to build a single process tool that used 2,000 threads running in parallel that allowed us to achieve a speed of about 1,000 domain names per second, and which was quite a good speed, which allowed us to scan all the 120 million domain names in about a day and a half. This speed can probably be further improved, but for us there wasn't a reason to do that because what we had was fast enough. And here are the results. Basically, almost 1/4 of all domain names didn't even respond, either because there was a problem with the DNS or because there was no server listening on either port 80 or port 443. So that's what left us with about 92 million domain names. And then we continued to drill into these results and narrow down the numbers as we go on further, because our goal for the survey is to find those certificates and SSL servers that are actually used and that people intended to use. So our logic was that if we look at certificates that we get and compare the name in the certificate with the domain name that we are looking at, and if there's a match between these two names, then we found a certificate that we can look into deeper. So we looked into the active domain names. Most of them, almost all of them, responded at port 80, and only about more than a third responded on port 443. But even those that responded port 443 didn't offer SSL. Only 2/3 actually had SSL running, and 1/3 had protocols other than SSL. This is not unusual because port 443 is usually open on firewall, so people use it for, it's very handy because it's always there. Most of these non-SSL servers are just plain text HTTP, although we have found quite a large number of secure shell servers there as well. Anyway, drilling down into the 22 million SSL servers, we just then extracted all the certificate names and then compared the names. And then we found that there's about 720,000 certificates where the names matched. And this is the data sample that's actually very useful to us and that we wanted to keep and use in the second phase of our study. Just as a way of comparing things, the pie chart on the right, donut on the right, is the same analysis of the Alex's top 1 million domain names. So you can see that, relatively speaking, almost 1/4 of all top 1 million websites actually have SSL, proper certificate names that match the domain names, which also makes sense because in our large sample, there are all sorts of domain names, most of which are probably parked. So the survey so far tells us a lot about the state of web hosting and virtual web hosting on the internet. If you look at the numbers, we're looking at 120 million domain names, but they're all represented by only 5 million IP addresses, which on average means that one IP address will host about 20 websites. And if you look only at those sites that support SSL, it's about 1 in 10. There's about 10 SSL sites behind the domain name. So this discrepancy and the large difference in numbers points to two burning problems with SSL. And one is the virtual SSL hosting is not possible. Virtual hosting is possible, and you can put as many websites on a single IP address. And this feature is what caused the explosion of popularity of the web. And it's very unfortunate we don't have the same feature for SSL. So today, to deploy a secure website, you actually have to have your own IP address and set up everything manually and do everything else that goes with that. More importantly, we are lacking a technical feature today to specify for a domain name if it supports SSL at all. And more importantly, we don't have a way for a website to say that it wants to support only SSL. Because right now, even if you have sites that want to support 100% SSL, there's nothing preventing browsers from trying to open a plain text connection to it. And in some cases, even that is enough for the secure connection to be compromised. So we need to look into how, there's already a feature for this, for this DNS server records, which are used for some protocols, but not currently for HTTP. Anyway, we're moving on. With some, so in the previous step, we had like 700,000 domain names. We looked at the 100 servers from the Alexa's top 1 million domain names. And we actually extracted quite a few domain names from certificates themselves. And by combining all this information, we basically arrived at about 860,000 known SSL servers that we wanted to look into. Because we know that there's about anywhere from between 1 million to 2 million commercial SSL certificates in the world. These are numbers, for example, given by Netcraft, who's been following the SSL market for a long time. The number of servers that we're looking at in this survey is from 25 to 50% of all valid SSL certificates on the internet. It's worth saying that the data set is probably very biased because we looked mostly at the top level domain names and not on the country specific ones. So as you may know, certificates will sometimes say, contain information about the organizations that own them. And so we extracted that information from where it was available. And you can see the chart there. For most certificates, we didn't know. The origin was unknown. But you can see that about more than 200,000 were US-based, and then followed by some from Japan, Great Britain, Denmark, and so on and so forth. Anyway, which sort of brings me to the main feature of the presentation, which is the results of the SSL survey itself. So what happened is that in the second phase of our survey, we actually needed more processing power. So in the end, we ended up using 3 servers, with 2 of them performing assessment in parallel, each server contributing about 2 to 3 assessments per second. And assessment would actually take quite a long time. We calculated the median value to be about 65 seconds. The network latency is what impacted assessment speed. So if a server is particularly close, we could complete the assessment in a couple of seconds. But for a server that's very far away, it may take even thousands of seconds. Anyway, what this proved is that, however, the resources that we used were pretty modest. And there was about 1 terabyte of the traffic that we used. All these 3 servers were virtual and quite modest when it comes to performance. So by far the biggest resources that we used was time. So, and I estimate that I've spent anywhere from 1 to 2 months full-time working on the study, making sure that everything works well, and validating results and fixing small issues and making sure that the results that we get are correct. So without further ado, let's move on. So if you recall, we had about 860,000 certificates. So in the first step, we wanted to look as to how many certificates we trusted. So trust is a somewhat subjective term. In our study, we used the trust base of Firefox 3.6, which means that Firefox will trust a certain number of root certificates which it has in the trust base. And the results here should be reasonably accurate and comparable to what you would get browsing using Firefox, although we did use slightly different technologies, so there may be some variations. And that's one thing else also that we discovered is with SSL, interoperability is still a problem, as I'll mention in a moment or two. So by far, we trusted about 70% of all certificates that we had in the database. But there's also a small group of suspicious. What we discovered is the interoperability problem. It seems that the Java implementation of SSL has some problem with certificate issued by a certain certificate authority. And so we think the overall number of trusted certificates is about 72%. For this test, I also did an independent analysis using OpenSSL, and we arrived to pretty much the same number. So it's about 72% of trusted certificates. If we look at the causes and why we couldn't trust certain certificates, by far the biggest problem was expired certificates. Either certificates that someone forgot to renew or those that were abandoned. The second was quite a large number of self-signed certificates, 96,000 of those, who are really not fit for public consumption, although they may be perfectly fine for those who know what these servers contain. And then the next is a similar problem, which is unknown certificate authorities. And this would be the case of people creating their own internal, perhaps, certificate authorities, which they would then use to sign certificates. And generally speaking, this group also is not fit for public consumption. There were about 20,000 certificates where we had interoperability issues, which we verified, and it's transpired that sometimes there will be sites that work with OpenSSL, but will not work with the Java SSL, but will maybe not work also with the Firefox SSL. So there are these issues that we will want to dig deeper in the future. There was a very small number of revoked certificates, only about 1,000, and there was a surprisingly large number of certificates whose subjects were malformed because they contained multiple common names. And I suspect these certificates were not issued by certificate authorities who would probably catch these problems. So these were probably self-signed too. Looking into expiry dates and validity of certificates, you can see that most certificates are valid for a period of 1 year, and then you can see spikes at 2, 3, 4, and 5-year ranges. And looking just at the expired certificate, by far the largest number of these have expired relatively recently, and so within a month or two, and then the number will go down rapidly, and it will just, you can still see that after 2 or 3, and even 4 years, there's a significant number of certificates that are still expired. And also looking at various problems, most certificates had only one problem, which is that they expired. But there's a number, about 38%, had some other problem too. And perhaps they were self-signed or issued by an unknown certificate authority and so on. Then we looked into the unknown issuers. And these were issuers that we couldn't trust because we couldn't find them in our trust base. And we realized that the great majority of these, there were about 43,000, we saw only once or twice, which means that someone generated a CA, and used it internally, and it's not a proper CA. There were only 22 certificate authorities that we saw more than 100 times, and I manually inspected every single one of them just to ensure. Of that list, I found 4 legitimate authorities, but they, CAs, for example, First Server Encryption Services is apparently a subsidiary of Yahoo in Japan, but it's not trusted by Firefox, and it's not trusted by other major browsers too. CA Cert is a certificate authority that is also not trusted, although they make an attempt to issue certificates and they have a long-term goal to be trusted. But you can see that they have quite a few certificates too. And there are 2 legitimate certificate authorities that are not trusted by Firefox, although they are trusted by other major browsers. And for what I could figure, they're not trusted only because they haven't completed the procedure where they would include their certificate into Firefox. Anyway, the point of this exercise is to make sure that we really trust only those certificates that we're supposed to trust, and that we're not missing a large number because of some internal problems. And then we looked into trusted issuers in the chain, the certificate chains. So normally, the way it works, you have each browser or SSL client will have a trust base. For example, Firefox has at the moment 155 of these. And those trust anchors will either sign web server certificates directly, or they will sign them to an intermediate certificate authorities. And the chain of trust can be of any size. But what we found is that, and the minimum size is 2. So in the table in the right lower corner, you can see the number of certificates that had a chain of particular length. So you can see that most certificates actually have the chain length of 2 and 3. And currently the chain length of 3 is recommended. That's generally because if you have a trusted anchor, the root certificate, you want to put it offline. You don't want to use it all the time to basically sign web certificates. So what you do, you generate an intermediate one, and then put that one online, so that can be used all the time. So one interesting point is that although we saw 429 certificate authorities, they only led to 78 trust anchors out of 155 that we had in our trust base, which is about only 50%. So even with Firefox, only 50% of trust anchors were used. So, and then we looked into these chains to see whether they're correct. We found that, strictly speaking, most of them are correct. And there's a small number of certificates of chains that are incorrectly formed for 2 reasons. There's often, so you can see about 6% of these are not correctly formed because they're missing intermediate certificates. So when you have a chain of trust, what you're supposed to do, you're supposed to include your web service certificate, but also include all the intermediate certificates, but not the final certificate, the trust anchor. So what we also found so some chains will be incomplete, and also in some cases the chains will be in incorrect order. The issue with this is not all SSL clients will know how to handle incomplete chains or chains that have incomplete orders. So these sites that do not have this implemented correctly can experience apparently intermittent problems with the SSL access that will be very, very difficult to troubleshoot. But there was one really unusual thing that we discovered, is that 43% of all sites actually send more certificates than they need to send. And those extra certificates will actually create a potential performance issue in bandwidth for them. So if we look into them, we can see a certificate is usually about 1 kilobyte long. So if you send an extra certificate, that increases the size of your SSL handshake by about 1 kilobyte. And what's very important about TCP connections is that initially they start off slow, and they sort of ramp up speed as the number of packets is exchanged. So the bottom line here, the sooner you complete the SSL handshake, the sooner you will start receiving actual data. If you have a handshake that's too long, then that will take more packets, and then the whole handshake will take actually quite a longer time. So you can see that quite a few of these certificates service send more certificates than they should, and no single. You can see in the table on the right, the first column displays the actual number that we saw, and the column to the right actually displays the number of certificates we should have seen. You can see that no server needs to send more than 5 certificates, but there was actually quite a large number of sites that send more, and there was even one site that sends 116. So this one site probably had a SSL handshake alone on 120 kilobytes of data, which is a tremendous number, which will slow down the handshake quite a bit. And this is just a matter of misconfiguration. It's something that can be relatively quickly, and just someone that needs to do that. Now, the reason I looked into this problem, and the reason why so many sites actually send more certificates than needed is because those are the instructions that they get from their certificate authorities. So I had a certificate that I used for some of my websites, and I saw that I had my site suffered for this problem because I just took the chain that was given to me by the CA and installed it in the server without really realizing that there's one certificate too many. Anyway, this is not going to be a problem for most sites, But for those sites who want to really squeeze every single bit of performance, they really need to look into this. The other thing they need to look at is session resumption. I have good news here, which is the majority of websites that actually implement session resumption well, and only about 10% don't, either because they have this feature disabled, or for some other reason they advertise the feature but they don't actually use it. And this is a problem because if you don't have session resumption enabled, then you have to establish a full SSL handshake for every single connection to your SSL server, and which basically takes a long time and will significantly slow down the performance of your website, and it will worsen the experience, the user experience. And I'm going to back to trust anchors, and now we're going to look into which trust anchors are actually used. I figured this is a slide that most people here will be interested in. Now, it's important to make a distinction. This is not market share. So, although some of these trust anchors that I have listed here are certificate authorities that issue certificates directly to end users, some of these may not be, and because they will only work with other intermediate CAs, or also some companies have multiple trust roots, and they will appear many times in the same list. But the point of this slide is to actually look as to how many certificate authorities do we need to trust. Because as you may know, there's a discussion in the SSL community because the size of the trust base is exploding. And the issue is that there's no delegation when it comes to certificate authorities. Any CA can sign any domain on the internet. So even some obscure CA that you've never heard about and that virtually no one uses can sign the certificate for the largest website on the internet. So that sort of erodes our trust in the whole system. So we can see that only this trust anchors that I have listed on this slide were used to sign 90% of all certificates that we had. So just as a reminder, this study is about 600,000 certificates that we trusted. So after we identified those that we could trust, we continue the study only with that sample because we know those were valid and we know those results will be meaningful. So this is the interesting issue. If we have 429 issuers, but we only saw 78 trust anchors, there's a relationship, and we can now build a tree and figure out which trust anchors actually have delegated authority to generate certificates. And you can see here the graph, and you can see that by far the largest number of issuers come from one trust anchor, which is owned by Deutsche Telekom. And we have seen 169 different certificate authorities leading back to just one, to their trust anchor. And then you have a couple of others, such as CyberTrust and UTN, having 48 and 29 delegated certificate authorities from them. So the thing is, this is in the sample of 600,000 certificates we did see, and I'm guessing that Deutsche Telekom will have a far larger number of these certificate authorities, but they're probably very rarely used, and you're only going to see them once in a while. And the question is that often on many people, many of those who deal with SSL is how many trust anchors do we need? And I made that calculation. So you can see here that with having only 11 trust anchors, you can cover about 90% of the 600,000 certificates that we looked at. By having 23 trust anchors, you go to 99.1%. And by having 42, you go to 99.9. Now, this is, of course, very subjective, and if you recall, our data set is skewed towards global domain names. So someone in Japan may have a different picture, and someone in some other country, perhaps people in different countries will have different certificate authorities that they use. So the exact number usually, so I reckoned that every one of us will need between 10 and 20 certificate authorities, but the exact number may vary depending on which site you visit. From here on, we stop looking into sort of certificate and issuers, and we look into the protocols and the quality of the connection. So, and this is where we go deeper into SSL and TLS. So the important thing about certificates is their keys, and most of these keys are using RSA, the RSA algorithm, and in fact we have found only 3 certificates that use DSA. The good news is the key size is usually good, and by far virtually all certificates will use a key size of 1024 bits, and then 2048 bits, and there's a very small number of sites that actually use any of these other numbers. So we also looked, if some of you may recall, in 2006 was a problem with the way certificates were generated on the Debian operating system, and the problem was only discovered in 2008, which basically made all those certificates weak. And we have discovered that there's only about 99 of these left among the trusted sites that we saw. So that problem is pretty much gone. Although interestingly, there are still some sites who haven't really replaced the certificates, and they are still very vulnerable. And basically, SSL doesn't work for them. Looking further is the support for multiple domain names. I mentioned earlier that there isn't a way to have virtual SSL hosting. And so the next best thing is to actually make your certificate be valid for multiple domain names. And there are multiple ways to do that. One is to use a wildcard certificate, in which case you have a certificate that's valid for any number of subdomains. But there's also the alternative names field, which can contain any number of domain names, and they can also be wildcards too. This is a feature that can easily be abused, as you'll see later on. But the idea is that the wildcard certificates should only be used for those certificates that stay within the same department or the same organization, where same people control all these certificates. Because if you have 2 departments sharing the same certificate, one department can subvert the SSL connections of the other one. So you basically share the trust, which is something that not many people realize. So we looked into these certificates. Most are not, only 4.44% of the certificates are wildcard, and most of these are wildcard because the wildcard is the common name, but 1.72% also had the wildcard in the alternative names. And most will have just 0, 1, or 2 of these domain names. And there's a small number of certificates that have a ridiculously large number of alternative names. So you can see on the top of the list is one that has 252 domain names. And then there are those that have 191, 153. But the certificate that has by far the largest number is one that we didn't trust, but has 354 different domain names. So this is clearly an abuse of the system. The issue with having so many domain names in the certificate, apart from the shared trust, is that the certificate grows in size, and if you recall, increases the overall size of the handshake, and then slows down everything. Another very important thing is that only 35% of all certificates were actually valid for the domain name with and without the www prefix. And this is very important because usually we as technical people will like to say, okay, the domain name is www.example.com. However, in real life, what you get is people just typing these domain names sometimes with, sometimes without. So if you don't have a certificate that supports both variants, then your users sometimes get confused. So it's a shame that only 1/3, well, slightly over 1/3 of certificates actually support this. So if you're, basically my advice in this area would be, if you're purchasing a certificate, just go to a certificate authority that will automatically make the certificate valid for both of these. On this slide, I have a bit of bad news, and this is by far the most disappointing finding of the survey, which is that more than 1/2 of all servers still support SSL2. And it's really saddening because we've known that SSL2 is insecure for about 14 years now. And you should think that 14 years is enough for people to realize that they shouldn't really be running SSL2. And actually, the number is higher. It's actually 65%, because we also looked into, even if you have SSL2 enabled, do you support any of the SSL2 cipher suites? Because if you don't support any of the cipher suites, the SSL2 connection cannot be made. So there's about 12% of servers that have SSL2 enabled, although they do not have any of the cipher suites enabled. The good news is, relatively good news, is that most servers will support SSL3 and TLS1, which are reasonably secure. Another bad news is that virtually no servers support TLS 1.1 or TLS 1.2. TLS 1.1 is a 2006 protocol, so it's been 4 years now. TLS 1.2 is a 2-year-old protocol. And there are good reasons why we have these protocols, because they correct certain problems with TLS1. In particular, TLS 1.2 is actually designed to solve the problem of the SHA hashing function being not being terribly secure, and basically needs to be phased out after 2010. And the best way to do this is to deploy TLS 1.2. So what we have here is, you can see that the protocols that are supported will depend pretty much on the protocols that are implemented by the libraries used by various platforms. And for example, OpenSSL, which is by far the most popular library, does not support TLS 1.2, and we don't know when it will. So we have the case where the security of the overall system really relies on the features supported by OpenSSL. I should also mention that in determining whether servers support SSL2, we also looked at those who will maybe accept an SSL2 connection, but only use it to deliver a user-friendly error message and refuse to actually do anything. And we didn't, so those were not classified as supporting SSL2. They were classified as not supporting SSL2. Then we looked into which ciphers, key exchange, and hash functions are used. And you can see that triple DES and RC4, as old as they may be, they still rule, and they're supported basically by virtually all servers on the internet. And then only after, so 99% of all servers support triple DES, 98% support RC4, and AES is only about on the third and the fourth place with about 68% popularity, which means that most of the internet is running on these older protocols, algorithms that are still secure. When it comes to key exchange, RSA is by far the most popular one, but we did see support for others as well. When it comes to hash functions, SHA is also very popular. And what is really worrying is we have seen almost no support for any of the SHA-2 family. And the SHA-1 family is essentially deprecated, and we really need to move on and stop supporting it in SSL servers. However, I doubt that will happen quickly, because from what we've seen so far. Cipher strength is the next aspect we looked into, and I have good news here, which is that most servers actually support strong ciphers, and most will support 128-bit encryption, and a large number will support 256. So if you look on the chart on the right, you can see that only 9 servers did not support 128-bit encryption. But 68 supported 256. And the pie chart on the left will tell you what's the best strength. And the best strength for the largest number of servers, 68%, is 256 bits, which is pretty good. And virtually everyone supports 128. So those are good news here. Mixed results when it comes to cipher suite support. Again, we have triple DES, and RC4 at the top of the list. And what we looked here is that there's a feature of SSL and TLS that allows servers to take responsibility and choose which cipher suite will be negotiated. However, it was disappointing to see that only a small number, relatively small number of about 40% of servers took the opportunity to choose and select which cipher suite will be used. The majority, about 60%, actually would use the first server offered, first cipher suite offered by a client. However, more worryingly, looking at those that did choose to exercise their choice, and that's what the table in the left lower part is, we can see that at the top of the list we have two RC4 ciphers, which are pretty good. We have a triple DES, which is so-so, and then AES. But what is worrying that we have three cipher suites here that are weak. We have one with just a 56-bit DES encryption, and we have two further cipher suites which use weak key exchange and also use weak encryption. So what is worrying here is that these servers are actually actively choosing bad cipher suites. So what leads me to conclude, at the moment, it's actually better to leave cipher suite selection to clients, because what I've seen in this survey so far is that browser vendors are actually far better today at choosing which protocols and which cipher suites to support. And whereas server side vendors, not as much. They will basically support all protocols because that's easier for them for interoperability. Because if you have your default settings that support all protocols and support all cipher suites, that's the best for them support-wise, but it's not best for us security-wise. And so this leads me to a slide which aims to summarize the survey so far, and which is where we basically assessed the configuration of every server and gave it a grade. And we discovered it's only about 1/3, or slightly more, 39% of all servers that were looked at are well configured. And I reckon these are the servers where someone actually actively looked at how they're configured and made sure they are configured well. And almost 2/3 of the internet, we have a pretty badly configured SSL servers, which are probably just running with default settings, which is pretty disappointing. So this is the point of the SSL service. So what we would like to do is identify these people that have badly configured SSL servers and get them to fix this, because it can take as little as half an hour after you identify a problem to find where SSL is configured and reconfigure it that you receive an A grade. We have actually had cases of people having invalid certificate, getting a certificate, purchasing a certificate, reconfiguring their SSL site, everything in half an hour, and getting a very good score. I have about 1 or 2 slides left at the end for SSL connoisseurs. This slide discusses strict transport security, which is basically the cutting edge of SSL. I mentioned earlier on that the only way for sites to be really secure is to support SSL for 100% of the content that they offer. So but at the moment, almost the best thing you can do, if someone talks to you on port 80, you have to just redirect them to the secure version of the site. And that is the single weakest point. If someone sends a link to port 80, if there's an active man in the middle attacker there, he can take that one single non-encrypted request and hijack it and use it to subvert the entire connection. And he can actually trick unsuspecting users into never going to a secure area of a website. So there is this feature which is called strict transport security, which is basically a way of a website saying, I only want to support SSL. And basically it gives instructions to browsers to never ever contact the non-encrypted area of the site at all. So what we have found is that among the 600,000 certificates, only 12 different sites supported strict transport security. So, which basically tells you this is how much people care about SSL today, and that we have a long way to go before the whole thing is made secure. My last slide with survey results is about secure and insecure renegotiation. And the problem with insecure renegotiation is the closest thing that we have discovered that's a flaw in the protocols. And it was discovered or made publicly announced late last year. And correct implementations have begun to appear about February this year. So what we have discovered is that at this time, there's about 1/3, 32% of all sites are still vulnerable to this particular problem because they support insecure renegotiation. Because I conducted several studies actually over a period of a couple of months, I can tell you that servers are currently patched at a rate of about 4% a month. So if you look at these charts, it's going to be at least 6 months before all the servers are patched. Well, that's probably never, all servers are probably never going to be patched, but it's going to be at least 6 months, maybe to a year, before we arrive to a reasonably secure state. So the other servers either do not support renegotiation, which is also secure if you can afford to turn it off, although not all sites can, and about 20% of sites actually support secure renegotiation. So those were the results of my study. I have a conclusion slide with a couple of thoughts that I want to leave you with, which is basically the good news is that virtually all deployments support good key sizes, good protocols, and good ciphers. The bad news is that most deployments actually support bad protocols, bad key sizes, and bad cipher suites. After 14 years, we still have SSL 2 deployed. And even more worryingly, we are not seeing people adopting new protocols, which means that maybe in a year's time, we'll find ourselves in a serious problem, and maybe with further discoveries of insecurities, maybe in the SHA algorithm, we may find quite a large number of servers vulnerable to different attacks. So it basically takes a really long time for servers to be patched. Long term, I think our biggest problem with SSL is the lack of support for virtual SSL hosting, and I think that creates a hurdle that prevents SSL to spread further amongst the website. And I think the final conclusion of the study is that so much of the security configuration depends on the default configuration that vendors ship with, and that we have to find ways to motivate them to ship with better default configurations, and we have to find ways to motivate library implementators to ship with better protocols and disable the bad ones. Anyway, to sum up, this is just the first step in our study. We've covered most of the stuff that we wanted to cover, but we would basically continue to conduct this study, I would say at least once a year, although don't hold me on that. And there are certain things that we want to improve in the future. There's one area at which we want to look deeper is to see how many sites will deploy partial SSL. And that is by far the most serious problem with SSL today. If you have a site that uses plain text, mixes plain text areas with SSL areas on the site, some sites even on the same page. Also the problem with insecure cookies. So for that part of the survey, we will have to crawl all these websites, which we'll probably do on a much smaller scale, but that will take a long while. And the good news is that all this research data that we've gathered, we intend to share and make available to the research community. So if they want to run their own queries against our databases, they can actually do that, so they can draw their own conclusions. And that's about it for me today. If you have any questions, I have about 5 minutes to answer them. 6,320. Yes. Just the certificate. So we looked into the Netscape variant and the Microsoft ones, and only 8% of the certificates supported it. We didn't test the actual upgrade process. Well, the bad ones are so bad protocols are those that contain. Yes, the question was about which protocols are good and which protocols are bad, and the bad ones that have known weaknesses, and that scientists have identified ways in which very specific ways in they are weak and in which they can be subverted. So for these other protocols, they may be weak as well, but we don't know it yet. And that's basically the way with crypto protocols anyway. All protocols are eventually going to be found to be insecure. And so we just have to keep moving on and upgrading to better protocols. So the question was about whether there were differences in configuration between different vendors. We haven't looked into it. It's very difficult to reliably, it's a minefield, first of all. And second of all, it's very difficult to reliably identify which operating systems and which libraries and which servers are actually running, because they're all configured differently. So we have collected the identifying information for what we could, and we also intend to fingerprint each of the engines running, so we could have more reliable data. But I don't have anything at the moment that I would be happy to release. Maybe, but you have to remember that Apache is used, OpenSSL is used by various web servers and possibly in different ways. So we couldn't really identify which version of Apache or maybe which distribution of Apache. So Apache running on Red Hat could be configured in one way, Apache running on Debian in another way. So then that's when the numbers will stop making any sense. So that's why we chose not to go into it, at least not at this time. Yes, sir. Yeah, the secure renegotiation means, yes, the TLS flaw has been fixed. So the implementation has been patched. It's a patch. So you basically patch your operating system and then you deal with it. That's how you deal with it. Go ahead. OpenSSL has been patched for secure renegotiation. However, not all Linux distributions, for example, have used the patch. So to the best of my knowledge, on Debian, you still can't be secure. But I think you can on Red Hat Linux and so on and so forth. Most platforms, their initial response, because it was 6 months before we had a solution for this problem, because the RFC had to be written, and the solution has to be, the committee had to come up with a solution. So the first action was to disable renegotiation. However, there's a very small numbers of sites that actually rely on renegotiation. Usually, if they support varying degrees of security and authentication within the same site, if they support client certificates, they do need renegotiation. So for them, there is no other way. But I think the large majority of sites can just disable renegotiation safely. I should also say that we are only able to test for client-initiated renegotiation, and there's also a server-based, which is not possible to test for. Okay? Thank you very much for being here. I hope you enjoyed the talk.